Hello and welcome back to Control System Lectures. In the last video I showed you the steps to designing a lead compensator using the root locus method. Now in this video we're going to design a lead compensator using the Bode Plot method. Now before we get started I want to make a quick statement regarding one of the driving reasons behind how I choose which information to put into these videos and which information I leave out. Now the math involved in classical control theory is very basic. Most of it can be done using solely algebra, the occasional dip into trigonometry, and only the easiest parts of calculus. So the question I have is, why is control theory so difficult to understand if the math involved is pretty straightforward? And I believe that it's really the concepts that are hard to grasp, not actually the mathematical steps that you need in order to find the answer. So with that in mind, let's go through the concepts of how to use the Bode plot to design a lead compensator. And I'll leave a lot of the math side of things to some of the textbooks and other references. And I've placed a few references in the description below if you're interested in checking them out. So let's get started. I'll set the problem up the same way that I did in the root locus video. You've got an open loop system and you've determined that it's not capable of meeting the system requirements. So you feed back the measured output, compare it against a reference signal, and generate an error term, which is then converted into an actuator command via the controller. And the compensation technique of choice for this controller is once again a lead compensator. And the question is, where do you place that single zero and that single pole in order to meet the requirements stated for the system? We know how to do this using the root locus method. First you convert the requirements into a dominant pole location in the S-plane, and then you set the zero and pole in such a way that the root locus goes through that specific location. The technique for the Bode plot method isn't much different. Here though, you start by converting your system requirements into frequency domain requirements, if they're not already there, instead of the pole locations in the S-plane. Frequency domain requirements are things like the following: phase margin, gain crossover frequency, bandwidth, and zero frequency magnitude value. There's also a requirement of steady state error, but this is kind of a time domain requirement, but it applies both in the frequency domain here and in the S domain on the root locus method. And we'll talk more about that in a future video. This in my mind is the hardest part of any compensation technique in the classical sense, figuring out where you want your poles in the S domain or how you want the open loop frequency response plots to look in the frequency domain. But once you know that, then designing the compensator to give you that look is mostly graphical in nature. Let me show you where these frequency requirements exist on a Bode plot for a generic second-order system. Phase margin is the difference between your phase and minus 180 degrees of phase at the point where the gain crosses 0 dB. And gain margin is the difference between your gain and 0 dB at the point where your phase crosses minus 180 degrees. The point where your gain crosses 0 dB is called the gain crossover frequency, and the point where the gain drops to minus 3 dB is called the bandwidth. The zero frequency magnitude, which is sometimes called the DC gain, is just the gain at very, very low frequencies, or zero frequency. In this case, for this plot, it's about minus 6 dB. So in the most simplistic explanation I can come up with, you're trying to bend and morph your Bode plot for your particular system so that it goes through these particular points at the requirements that are set for your system. So let's see an example with this. Let's design a system that has a steady state error of less than 0.02 to a unit ramp input. And the system also has to have a phase margin of greater than 48 degrees. So basically this red line needs to be longer than 48 degrees for our particular Bode plot once we're done designing our compensator. And we'll also say that we're given this exceedingly boring plant, which is 1 divided by 0.2s plus 1. Now whenever you're given a steady state error requirement, the very first thing that you should always check is the system type. Check out my video on final value theorem and steady state error for more information on this. But the system type is the number of poles at the origin, and this number dictates whether you're going to have infinite steady state error, finite steady state error, or no steady state error based on the type of input signal. So in our case with a unit ramp input, in order for the system to have a finite steady state error, then the system needs to be at least type 1, or a single pole at the origin. And if it's a type 2, it'll have 0 steady state error. Right away we can tell that this system is type 0 since it has no poles at the origin and therefore cannot meet the steady state requirement with a lead compensator alone. And that's because a lead compensator isn't going to add a pole at the origin. And since we need less than 2% steady state error, at the very least we need to add a single pole at the origin to make this a type 1 system. Now if you forget this step and you design a lead compensator to meet the phase margin requirement first, then you try to add a pole at the origin at the end to meet the steady state requirement, you're going to mess up the phase margin and have to start all over. So always start with the system type. Also, we could have added a second pole at the origin to decrease our steady state error to 0. But this would be an over-designed system and possibly bad in the long run. The reason I say this is because adding poles aren't free. It adds complexity to your design, complexity to the hardware to build it, and can reduce stability in your system. Since the requirement for steady state error is less than 2% and not 0, you'd be better off just meeting the requirement in most cases rather than exceeding it. So let's close the loop around our plant and our single pole here, and we'll also add a gain in line with it. And now we can move on to step 2, which is choosing the gain necessary in order to meet our steady state error requirement, which in our case is less than 0.02. Now you'll recall that the equation for steady state error is the limit as s goes to 0 of s divided by 1 plus g of s times the input r of s. And for us, g of s is the plant times k divided by s. And r of s is a ramp input, or 1 over s squared. And you can plug all of these values in and then solve for the value of k that makes this equation less than 0.02. And what you'll find is k needs to be greater than 49. So just to make the math simple, I'm going to choose k equals 50 for our control system. And I'll plug that into our block diagram for k. So now we know that our system meets our steady state error requirement, but we don't know yet whether it meets our phase margin requirement. And in order to figure that out, we need to plot the Bode plot for our open loop system. You can estimate this by hand by taking the Bode plot of the plant and adding it to the Bode plot of our compensator, k over s, or 50 over s. But I wanted something accurate, so I plotted it up in MATLAB, and I'll put it right here. To determine the phase margin, find the gain crossover frequency, follow that down, and then measure the distance between your phase and minus 180 degrees. Also, MATLAB shows me up here at the very top at the title that I have 18 degrees of phase margin. And 18 degrees is less than 48 degrees, so we don't meet our requirement. So we're going to need additional compensation, and that's where our lead compensator comes in, to give us that additional phase margin. The basic premise is this: try to move the phase curve upwards so that you can increase your phase margin without disrupting the magnitude plot too much. And to see how this is accomplished, let's look at the Bode plot of a typical lead compensator. So you can see that we're adding phase for a certain frequency band. And if you design the lead compensator correctly, when you add that phase gain, it'll cause the phase to go right through our new phase margin point that we want. And this is exactly what we want. Unfortunately, we're also adding a little bit of gain too. What that does is it moves the gain crossover frequency to a higher frequency, which means that you're not getting the full amount of phase that you were expecting because our gain crossover frequency goes through a different portion of the phase plot. So now you can see why this is graphical in nature. We're just adding these two Bode plots together to get one that we want in the end. But to determine how much phase we need to add and at what frequency, we're going to need some equations. And let me first start by showing you an equation for a lead compensator, written in a slightly different format than you might have seen. This is A2 times tau s plus 1 over tau s plus 1. And I like this form because it's easy to see that the zero frequency gain is 1, which means it's not going to disrupt our steady state error that we did in steps 1 and 2. And of course, in order for this to be a lead compensator, A2 has to be greater than 1. If it's less than 1, then it's a lag compensator, but we'll talk about that later. And you can determine the upper cutoff frequency with this equation, which is approximately where the gain and the phase start to head upward, and the lower cutoff frequency with this equation, which is the tail end of the phase and where the gain starts to flatten out. Phi max is the maximum amount of phase lead that the compensator can provide, and omega max, or omega m, is the frequency at which that maximum phase occurs. And lastly, the gain at omega m is given by this equation. So with these equations, you can solve for A2 and tau, which are the only two unknowns in our lead compensator, like this. Step 1 is choose the amount of phase that you want to add to your system and then solve for A2 using the phi max equation. And then determine the frequency that you want to add all that phase to, and then you can solve for tau using the omega m equation and the previously solved for A2. And then finally, you can just construct your lead compensator by plugging in A2 and tau, and you're done. But wait a second, there's a catch, and I've already mentioned it a little bit earlier. Remember, we can choose the phase that we want to add to the system, but again, it's going to add gain to the system at that frequency as well, which is going to move the gain crossover frequency to the right, which means you're not going to get that maximum phase increase. You're really only going to get something slightly less than that. So you're not going to meet your requirements still, and then this is going to ensue a potentially infuriating iteration where you try to add even more phase lead and see if that did the trick, and then add more and then more until you're done. But there are at least two ways around this. The first is just to add a safety factor to your original phase lead, so you only have to do this once. Something like phi max equals the phi that I need plus something like 15 degrees. And the second way is to just try a bunch of different values of A2 and construct a table and then just pick the correct value from the table after you're done. And I agree that neither way is really an attractive way of generating a lead filter, but it works. And sometimes control design is an iterative process and you just can't get away from that completely. Now I'll show you the final lead compensator for this system that I built up, but I think it's a good exercise for you to work out one on your own. And there isn't a one-size-fits-all solution here, so you'll probably come up with slightly different values. For me, I chose 37 degrees for phi max, which works out to A2 equals 4. And omega m at 22.2 radians per second, which works out to tau equals 0.022. And now I can lay this lead compensator in line with the other compensators, and this is going to make up the entire controller. And we can see that we meet our phase margin requirement by plotting the Bode plot for this fully compensated system. And I did that Bode plot in MATLAB, and I'll show you that here shortly. But I also overlaid it on top of the Bode plot for the system without the lead compensator so you can see the effect. And here it is. So again, we find the gain crossover frequency, and now you can see that the phase at that frequency has increased a lot. In fact, our phase margin is met. It is greater than 48 degrees like we wanted. And the other good news is that the magnitude plot looks pretty much the same, except for high frequencies. And we've only barely moved that gain crossover frequency to the right a little bit. So it all worked out, which is pretty awesome. So I think it helps to think of the lead compensator, at least in the Bode sense, as just a delta to your original uncompensated Bode plot. And you just need to try to manipulate your lead compensator Bode plot shape so that when you add it to your original one, all of your requirements are met. There's one last thing that I wanted to say, and that's that you can only add up to 90 degrees of phase with a lead compensator. That's because there's only a single zero in the compensator. But realistically, with how you implement a phase lead compensator with your components, you really should only ever try to add about 55 degrees with it. Anything more than that and the component values that you need become too large or too small to be practical. Therefore, if you need more phase lead than 55 degrees, you'll need to add two compensators, or two stages, in series, and they're going to add on top of each other. So you can get up to 110 degrees of phase lead if you have two in series. If you guys have any questions or comments on what I've said here, leave them in the section below and I'll try my best to answer them. And as always, thanks for watching.